Hello, this is our next topic, electricity and Coulomb's law. So at the end of this topic, you shall be able to do the following. All right. So let us recall from our previous topics, we have these fundamental forces in nature. We have already discussed what gravitational force is. In your chemistry for engineers, weak forces and nuclear forces are also discussed. So now we go to this fourth fundamental force in nature, which is the electromagnetic force. So if gravitational forces make objects with mass accelerate, then the electrical forces are the ones that make electrically charged objects accelerate. So electromagnetic interactions involve particles that have a property called electric charge, an attribute that is as fundamental as mass. Okay, so the word electric was derived from the Greek word electron, which means amber. So before, in ancient Greece, they discovered that after they rubbed amber with wool, the amber could attract other objects. So we have these pictures on the right side of the screen. So we have the first part, interaction between plastic rods rubbed on fur. So plain plastic rods neither attract nor repel each other. So that was their observation. But after they rub the plastic rod with fur, they observe that the rods repel each other. Okay, so the second part, we have glass rods rubbed on silk. So at first, there is no interaction. They neither attract nor repel each other, but when they are rubbed with silk, they repel each other. And then for part C, so one charged plastic rod and one charged glass rod. So if they are brought near to each other, there is a different effect in different interaction. So they observe that the two attract each other. So this is a bigger picture. So during this time, a person named Benjamin Franklin suggested calling the two charges positive and negative. So this is their conclusion. Two positive charges or two negative charges repel each other. And if you have two opposite charges, one positive and one negative, the interaction is different. So they attract each other. So as we know, in an atom, we have these three subatomic particles, electron, proton, and neutron. So these are their charges and their masses. So charges in coulombs with the capital letter C, and then masses in kilograms. These are the SI units. So if we have conservation of mass, we also have conservation of electric charges. So it says that the algebraic sum of all the electric charges in any closed system is constant. Thus, in any charging process, charge is not created nor destroyed, so it is just transferred from one body to another. And we have also to take note that the magnitude of charge of the electron or proton is a natural unit of charge. Again, the unit is in coulombs. So we have these classifications of materials depending on their ability to make electric charges move freely within them. So if the electric charges move freely in response to an electric force, such as what happens in copper or aluminum or silver, then the material is called a conductor. So when a conductor is charged in a small region, the charge readily distributes itself over the entire surface of the material, since the charges can move freely in response to an electric force. So if the charges cannot move freely in response to this electric force, then it is called an insulator. So glass and rubber are some examples of insulators. The third classification is semiconductors. So from the word semi, so it's between a conductor and an insulator. So the characteristics of semiconductors are between those of insulators and conductors. Silicon and germanium are some examples of semiconductors. Next, we have these types of charging. We have conduction, induction. Okay. So for conduction, charging by conduction, this is the summary of what happens to the charges. So first, so before contact, the negative rod repels the sphere's electrons, inducing a local positive charge. Okay, so we have a neutral neutral sphere here. So we have the same number of positive and negative charges, and we have a charge rod here. So before contact, so the negative rod repels the sphere's electrons. After contact, so if you are going to put the rod to in contact to the surface of the sphere, so the electrons from the rod flow onto the sphere, neutralizing the local positive charges. As you can see, there are no more positive charges because they are already neutralized by the negatively charged rod. And then when you remove the rod, so the negative charge remains on the sphere. So the two are now negatively charged. So this is charging by conduction. So the object being charged is always left with the charge having the same sign as the object doing the charging. So if the object doing the charging is positively charged, then the object being charged would be positively charged after you perform the conduction process. So the next type is induction. So when an object is connected to a conducting wire or pipe buried in the earth, it is said to be grounded. So a neutral sphere, same with the conduction earlier. So we have a neutral sphere, same number of electrons and protons. So if you are going to put a negatively charged rod near to an uncharged sphere, so same with the conduction. Okay, so the charges in the sphere are redistributed. So instead of touching the rod to the surface of the sphere, okay, induction is when you have a grounded conducting wire connected to the sphere. So the region of the sphere nearest the negatively charged rod has an excess of positive charge because of the migration of electrons away from this location. Okay, so this is what happens if you will put the negatively charged rod close, okay, but not touching the sphere. Take note. So close, no, it is brought near or close to the sphere. So if there is a conducting wire connected to the sphere and is buried in the earth, so it's grounded. So it allows some of the electrons to move from the sphere to the ground. So from the sphere to the ground. So what happens is that the excess positive charge is non-uniformly distributed. So the wire, if you remove the wire to ground, so the sphere is left with an excess of induced positive charge. So there is induction happening. So induced positive charge. So initially, the positive charge in the sphere is non-uniformly distributed. So if you're going to, again, connect the sphere to a grounded conducting wire, so instead of making the sphere negatively charged, so what happens to the conduction process, instead the the sphere now, okay, has excess positive charge. So the positive charge is induced. So eventually, the excess positive charge becomes evenly distributed due to the repulsion between the positive charges. So since there are many positive charges here compared to the negative charges, so there will be more repulsion than attraction. So charging by induction requires no contact with the object inducing the charge. So in 1736 to 1806, so there's another person who studied electromagnetism, so electrostatics and magnetism. And also, by the way, he investigated strengths of materials. Okay, so not only on the smaller scale, on atoms, on electrons and protons and neutrons, but also for the macro scale, so the forces acting on beams. So he is Charles Coulomb. So the SI unit of charge is named after him. So we have Coulomb's law, which states that an electric force has the following properties. So if we have a gravitational force or a tensile force or applied force from our previous topics, so here in electricity, so we have what we call electric force. So these are its properties. So it is directed along the line joining the two particles, if you're talking about a force between two particles, and inversely proportional to the square of the separation distance between them. It is proportional to the product of the magnitudes of the charges Q1 and Q2 on the two particles, and it is attractive if the charges are of opposite sides and repulsive if charges have the same signs. So to summarize, we have this mathematical equation. So electric force is equal to the K sub E times Q1 times Q2 over the square of R. So K sub E here is called the Coulomb constant, and this is its value. So its unit is Newton meter squared per Coulomb squared. So there are some authors, no, some references that are using 9 times 10 raised to the power of 9 instead of this more accurate value. So typical charges can be in the microcoulomb range. So since we are talking about a force, so we have to remember that forces are vector quantities. So direction is important. And this law applies only to point charges and spherical distributions of charges. This is the limitation. And R is the distance between the two centers of charge. Okay. So for example, if we have these two positive charges, Q1 and Q2, Q1 and Q2. So since they are of the same sign, they are both positive, so the force is repulsion. Okay, so this is the R, the distance, okay, between the two spheres. Okay, and then these are the forces acting on Q1 and Q2 respectively. So F sub 21 means that it is the force that is acted on Q1 by Q2. So 2 is doing the force to Q1. And then we have this second arrow. So it's 1 to 2. So meaning it is the force that Q1 is acting on Q2. Okay. Remember that in writing free body diagrams, so the arrows of the forces acting on an object should be drawn from the object. So since this blue arrow is drawn from Q2, then this is the force that is acting on Q2 by Q1. There's no other object around, so Q1 must be the charge that is doing the force to Q2. Okay, so again, 2-point charges are separated by a distance r. The like charges produce a repulsive force between them, and the force on Q1, meaning F sub 21, is equal in magnitude and opposite in direction to the force on Q2. So these two are equal in magnitude but opposite in directions. So if we have charges that are opposite, so the force is called attraction. Okay? So this is the force that Q2 is acting on Q1, and then this one is the force acting on Q2 by Q1. So since it's attraction, so the direction of the arrows are towards each other. So we have what we call superposition of electric forces. So what if we have one charge and then there are many other charges surrounding it? So we superpose, or we have superposition of electric forces rather. So Coulomb's law, again, its limitation is it's applicable to point charges only. And take note, it should be 4-point charges in vacuum. So no other forces are considered here. So only the forces between the charged objects. Okay. So it's like from our previous topic that we neglect air resistance. Okay. So here we neglect other forces. So we just focus on the electric forces. So if matter is present in the space between the charges, the net force acting on each charge is altered because charges are induced in the molecules of the intervening material. So we assume that there are no other particles, okay, or anything between these charges, because for sure there will be an effect on the forces acting on the charged particles. So as a practical matter, though, we can use Coulomb's law unaltered for point charges in air. Because at normal atmospheric pressure, the presence of air changes electric force from its vacuum value by only about 1 part in 2000. Okay, so we can also assume that these charged particles are not in vacuum but in air. Okay, so we assume that the effect would be negligible since it's only about 1 over 2000. Okay. So when two charges exert forces simultaneously on a third charge, the total force acting on that charge is the vector sum of the forces that the two charges would exert individually. So this property, called the principle of superposition of forces, holds for any number of charges. So when two electrically charged particles in empty space interact, so assume that they are in empty space, how does each one know that the other is there? Okay, so how will we know that there's another charged particle near or a few few micrometers away from one particle. So it's because of this particular quantity called electric field. So just a little trivia. So sharks have the ability to locate prey that are completely hidden beneath the sand at the bottom of the ocean. So this is due to the the what do you call this ability of the shark to sense weak electric fields produced by muscle contractions in their prey. I think kuan man na siya no kanang sa mga salida no that if a shark is near you then mas okay if you will not move. So that's true because they can sense that there are kuan prey around them. So manandi ka mulihok para di ka kanon. So sharks derive their sensitivity to electric fields from jelly-filled canals in their bodies. So kaning mga kuan diri na so pores niya sa shark. So these canals end in pores on the shark's skin. Okay, so a weak field, electric field causes the charge flow within the canals and trigger a signal in the shark's nervous system. So masense niya nga, uy, na ko'y pagkaon. Okay, so as weak as so nawala no so the value here is lost. So I'll just comment it in the post no kung unsay value ani. So basta a very weak electric field can be sensed by a shark. So that's the same concept in two charged particles. So we will know that there's something near, okay, or within a certain region. Okay, there are more particles, two or more particles within that region because of the electric field. So a charged body creates an electric field in the space around it. So let's say these are the charged bodies. So we have A and B. Okay, so A is more positively charged compared to B based on the number of positive signs here inside the spheres. So since they are of the same sign, they are both positively charged. Okay, so the forces acting on them are opposite in direction but equal in magnitude. Okay, so we'll know that there is something around a charged body because if we remove the B and label its former position as P, okay, so there would be something, okay, happening here. Now, of course, they observed that using some instruments, okay, many years ago, manailahang experiment. So if we remove the particle, no, the particle B, so they observe that there is a force that is exerted by A on a test charge Q sub O at point P. So this force is what they call electric field. So the electric force on a charged body is exerted by the electric field created by other charged bodies. So at this point, okay, A is exerting a certain force over this area here, over this test charge. So the force on a positive test charge points in the direction of the electric field. So the force is in the same direction with the electric field because of the presence of this charge on the left side. So the direction of the electric field and the force are opposite if the test charge is negative. Okay. So as you can see, the direction of the electric field is away from the charged particle here, the test charge, what we call the test charge. Okay. So if the two particles are of the same sign, then the direction of the electric field is the same with that of the force. And if the test charge is negative, so the two are not the same sign, then the directions of the force and the electric field are opposite. So the electric field at a certain point is equal to the electric force per unit charge experienced by a charge at that point. So here's a mathematical equation. Okay. So the electric field, if you're going to transform the equation so that the variables present are the Q, the electric, the Coulomb constant K, and then the R. So from the Coulomb's law mathematical equation, okay, we replace this electric force with K times Q sub O, okay, or Q1 and Q2. So we just replace Q1 and Q2 with Q and Q sub O respectively. And then over R squared, then divided by QO, Q sub O. So we cancel out the common variable Q sub O. So we end up with this mathematical equation for electric field. So in terms of the charged particle Q and the separation distance between the particle and the test charge. So we also have superposition of electric fields. So we just get the resultant of the electric fields. Same as in getting the resultant of the electric forces. So if, for example, we have this particle Q sub 1, so there is electric field, okay, and at this specific point, point P, there is this arrow here. Okay, it is drawn away from point P. And then we also have another charged particle. This time it's negative. So we have another arrow. So this is E sub 2. So the electric field caused by Q sub 2. So we label it as E sub 2. So we get the total electric field at this point P by getting the resultant of E sub 1 and E sub 2. Okay, so we get the vector sum. So we have example number 1. So force between 2-point charges. So we have Q sub 1. Okay, so let this be Q sub 1. It's positively charged. So Q sub 1 is 25 nano coulombs, or that's times 10 raised to the power of negative 9. Okay, 25 times 10 raised to the power of negative 9 coulombs. And then the second particle is negatively charged. Okay, so it's Q sub 2. Its magnitude is 75 nanocoulombs. So the separation distance is 3 cm. So R is 3 cm. So by the way, the separation distance should be measured from the centers of the two particles. So R is 3 cm. So find the magnitude and direction of the electric force that Q1 exerts on Q2 and that Q2 exerts on Q1. All right. So we have Letter A, Q1 exerts on Q2, so it's F sub 1, 2. And for letter B, it's F sub 2, 1. But we know that these two are equal in magnitude but opposite in direction. Okay, so regardless of the magnitudes of the charges, the forces acting on them are equal in magnitude. So since the two are positively and negatively charged, so the attraction, the force would be attraction. Okay, so the arrows representing the forces should be towards each other. So for Q sub 1, the arrow that we are going to draw is to the right because Q2 is to its right. Okay. So this is the force. Sorry. This is the force that Q2 is acting on Q1. And that is the same force that Q1 is exerting on Q2. So same in magnitude. So we have to solve for that value. So this is the force that Q1 is acting on Q2. So again, they are equal in magnitude but opposite in direction. Okay, so that's why we need the absolute values of the charges. Okay, so we disregard the negative sign of Q2 later when we do the computations. It's because of the direction. Okay, the direction of these forces. So, so that it will not be confused with the charge of the particle. Okay, so the negative sign later for the force. Okay, if we remove the absolute value symbol in the computation, so if we get a negative sign, it doesn't mean that the force is to the left, and if positive, the force is to the right. So it has something to do with the with the type of force, whether it's attraction or repulsion. Okay, so para dili ma-confuse with the direction and the type of force, so we use the absolute value symbol. So solve for F sub 1, 2, which is again just equal to F sub 2, 1. Okay, so it's K or K sub E or just write K. And then times absolute value of Q1 times absolute value of Q2, then over R squared. Okay, or you can just put K together with Q1 and Q2 on the numerator of this fraction. Okay, so let's use the 9 times 10 raised to 9 Newton meter squared per Coulomb squared. And then the absolute value of Q1. Okay, or you just remove the negative sign for Q2 later. So it's okay if you don't write the absolute value symbol. Just don't forget the meaning of that symbol. So you can just write 25 and then you use the SI, or rather the SI unit already, the base unit. Okay, which is in coulombs. So nanocoulombs is times 10 raised to negative 9 coulombs. Then for Q2, again, you don't copy the negative sign. So it's also in nanocoulombs, so negative 9 coulombs. And then all over R squared. So R is in cm, by the way. So we need to convert that into meters. So in 1 meter, there are 100 centimeters, and it should be squared. So after converting it, you need to square it. Or you convert it first, 3 over 100, or 0.03, and then square the value of R. So the electric force exerted on the point charges is, okay, so that's 9 times 10 raised to the power of 9 times 25 times 10 raised to the power of negative 9 times 75 times 10 raised to the power of negative 9, and then divided by, so that's quantity 3 divided by 100, and then square it. So it's 3 over 160 or 0.01875. So the unit is, okay, we cancel out the columns, and then we have meter squared. So it will be canceled out with the meter squared here. So what we have is only the unit of force, which is newtons. So this is the force that Q1 is acting on Q2. And also the same force that Q1 is acting on, or rather Q2 is acting on Q1. So it's the same. And again, magnitude. Okay. And it says here magnitude and direction. So for F sub 1, 2, okay, so it's to the left, or it's much safer to say that it's towards Q1. And for F sub 2, 1, it's towards Q2. Okay, so if you will say to the left or to the right, so we can swap the locations or the positions of Q1 and Q2, right? We can put Q2 on the left side and Q1 on the right side. So the arrows would be different na ang direction. So it would be best to express the directions in terms of towards or away from Q1 or away from Q2 if ever the force is not attraction. All right. So the second example, okay, so we have some positions here. So 2-point charges are located on the x-axis of the coordinate systems. Basically the same with example number 1, except that we need to solve for r. Okay. So if Q1 is 1 nano Coulomb, so meaning it's positively charged. So this is, let's say Q1. So 1 nano Coulomb. And it is at 2 centimeters. Okay, so there is a reference point. The 0 cm mark is not the position where Q1 is. So this is the 2 cm mark. So let's say the 0 cm mark is here. Okay, so 0 cm. So the second point charge, which is negatively charged, negative 3 nanocoulombs, okay, or Q2, it is at 4 cm. So 4 centimeters away from the reference point. Okay, so let's say this is Q2, so it's negatively charged. Okay, so it's negative 3 nanocoulombs. Okay, so the location is at positive 4 centimeters. So what is the total electric force exerted by Q1 and Q2 on a charge Q3, okay, which is at x equals 0. So here at 0 cm, there is another force, another charge there. Okay, so which is positive, it's 5 nanocoulombs. So here we have a positively charged particle. Okay, so it's 5 nanocoulombs. So what is the total electric force exerted, okay, on Q3? So we need to draw the free body diagram of Q3. So we have two charges okay, near it. So Q1 and Q2. So meaning we have to draw two arrows from Q3. So since it is positively charged and then Q1 is also positively charged, so the force of attraction would be repulsion. Okay? So it's repulsion meaning so the arrow should be drawn away from Q1, right? It shouldn't be towards Q1 because that would be attraction. So it's repulsion. So draw the arrow, okay, away from Q1. So this is the force that Q1 is exerting on Q3. Okay. Then for Q2, its effect on Q3 would be attraction. Okay. So this is negatively charged. Q3 is positively charged. So the force between them is attraction. So the arrow that should be drawn from Q3 to represent the force acting on it by caused by Q2. So should be kani to the right. Okay, towards Q2 since it's attraction. Okay, so using the violet pen. Okay, so this is the force that Q2 is acting on Q3. Okay, so we need to get the total electric force. Okay, so we have to solve for their magnitudes. First, solve for F sub 1, 3. Okay, so we need, by the way, you can put Q1 times Q2 inside this absolute value symbol. So instead of putting two absolute value symbols for Q1 and Q2. Okay, so you can just get the product and then get the absolute value symbol. So it's the same with the other way of writing it. Okay, but some point is we remove the negative sign. Okay, so over r squared. So this is for 1 and 3, by the way. So this is 1 and 3. And the separation distance must be between 1 and 3. Okay. So that's between 0 and 2 cm. So r sub 1, 3. Okay, let's just put it here. R sub 1, 3 is 2 cm. Okay, so plug in the value. So we have 9 times 10 raised to the power of 9 Newton meters squared per Coulomb squared for the Coulomb's law constant. And then times the absolute value symbol of Q1 times Q3. So that's 1 times 10 raised to the power of negative 9 coulombs. Okay, times 5 times 10 raised to the power of negative 9 coulombs. Or you can just remove the absolute value symbol. And then 2 cm, okay, convert that to meter. So instead of putting the conversion here, so let's say I'll convert it before plugging it in the equation. So you can just put here the converted value. Okay, so it's 0.02 meter because it's 2 over 100, right? So we have 0.02 meter quantity squared. So the force that 1 is acting on 3 is, it's 1 instead of 25. Then it's 5 instead of 75. Then we have 2 over 100. Or let's just put 0.02. Okay, so it's 9 over 80,000. Okay, or that's 1.125 times 10 raised to the negative 4. That's in newtons. Okay, so the direction is away from Q1. So we can put the negative sign later. Okay, because from the drawing, from the diagram, so it's pointing to the left. So we assume that that's a negative force. Okay, so F sub 1, or rather 2, 3 would be next. So for F sub 2, 3, so it's K times Q2 times Q3, then over the separation distance between 2 and 3. So R sub 2, 3, so that's between 0 and 4 cm, so that's 4 centimeters, or in meters, it's 0.04. So plug in the values, the Coulomb's law constant, and then we have times, so Q2, so just remove the negative sign. Okay, nano columns, and then Q3 is 5 also in nano columns, and then all over 0.04 meters quantity squared. So we have 3 and 5, also 5, then 0.04 for the distance. So it's 27 over 320,000, or 8.4375 times 10 raised to the negative 5. In newtons. All right. So the direction is towards Q2, right? So we use positive value for F sub 2, 3 and negative value for F sub 1, 3, okay, to get the total electric force. So solve for F total. So F total would be, okay, the summation of F sub 1, 3 and F sub 2, 3. So they are just located on the same axis. So you just add them algebraically. So again, for F sub 1, 3, so let the direction be negative. Okay, to the left. So it's negative 1.125 times 10 raised to the power of negative 4 newtons. And then for F sub 2, 3, let that carry the positive sign because it's to the right. Okay, so plus 8.4375 times 10 raised to negative 5. So add them. It's already here on the screen. Okay, the F sub 2, 3 value is already on the screen. So just put minus 1.125 times 10 raised to the power of negative 4. So the total force is negative 2.8125 times 10 raised to the power of negative 5. Okay, newtons. So that means that the magnitude is 2.8125 times 10 raised to the power of negative 5, and the direction is away from both Q1 and Q2, right? Because it's to the left. So magnitude is 2.8125 times 10 raised to the negative 5 newtons, and the direction is away from Q1 and Q2, right? So for example number 3, this time it's not located on the same axis because we have some y values here. Okay. So just the same with two-dimensional motion. Okay, so we get the total forces along the x-axis and total forces along the y-axis, and then get the resultant. Okay, so let's have that. So two equal positive charges, Q1 equals Q2. So they are both positive and equal in magnitude also. So 2 times 10 raised to the power of negative 6 for microcolumns. So they are located at 0, 0.3 for the first one. So let's say this is the origin, 0, 0. So 0, 0.3 is, let's say, here. Okay, so let this be Q sub 1. So it's 2 microcolumns. And then the second charge is at 0, negative zero point 0.3. So it's below the origin. Okay, so it's also positively charged. Okay, so 2 microcolumns also. Then, what are the magnitude and direction of the total electric force that Q1 and Q2 exert on a third charge, capital letter Q, which has a magnitude of 4 microcolumns and is located at 0.40. So 0.4 meter 0. So that's along the x-axis. Okay. So it's somewhere here. So it's negative. Oh, it's also positively charged. So let's say this is the Q with magnitude 4 microcolumns. So we have to get the total charge, okay, total force rather, that Q1 and Q2 exerts on Q. Okay. So first we draw the arrows representing the forces acting on Q. So between Q1 and Q, so both are positive, so the force is repulsion. So the arrow should be drawn away from Q1. Okay. And it should be in the same line with with the distance between the two. Okay. So along this axis. Okay, so let this be the force that Q1 is acting on charge Q. And for Q2 and Q, for the blue force, so both are positive, so it should be drawn away from Q2. Okay, so we have this force, okay, for Q2 to Q. So we have to get the vector sum of these two forces. Okay, so again, we get the forces along the x-axis and forces along the y-axis and get the resultant. All right. So if we have a two-dimensional force here, so we need the angle. Okay. So for the angle, so it's actually this angle here. So let me draw that again. Here na lang, below the first drawing. Okay. So let me just use a point to represent Q. Then draw this axis here. So the F sub 1 Q is this arrow here. Okay. So we need this angle here. Okay. Or if we'll use the standard position of the angle, so we need this angle here. Okay. But we don't know what's this angle if we don't know the one inside. Diba? So the inner angle. Or you can also measure it from the y-axis, but to be consistent with the cosine and sine components, so use the standard position of the angle, so measured from the x-axis. Okay, so we can draw a triangle. Okay. from this drawing. No, let me complete the right triangle by putting this line segment here. So this is a right angle here. Okay, so we have that triangle, okay, whose length is actually, okay, so if we will base it from the origin, so it's actually the same triangle here. Okay, so this angle here, okay, is the same angle here. Okay, so let's say this is angle theta. So solve for angle theta. So this is 0 to 3 meters. So this is 3 meters. And then this is 0 to 4 meters. Horizontally, the distance, okay, is 4 meters. So we can get that angle. Okay, so solve for angle theta. So theta would be, okay, so that's opposite over adjacent. So that's tangent. So theta is arctangent of the opposite side, which is 3 meters, and then over the adjacent side, which is 4 meters. So our tangent, okay, arctangent of 3 over 4. So that's 36.8699 approximately. 8699. 8699. Okay, degrees. So it's the same angle here. So if we'll use the standard position, so that would be 360 degrees minus 36.8699 degrees. So that's 360 minus the answer. So 323.1301 degrees. Okay, so this is the angle for F sub 1Q. Okay, so next would be the F sub 2Q. Okay, the angle for F sub 2Q. So basically, it's a similar angle. Okay, so it's pointing on it's located in the first quadrant. So actually, that angle, okay, is the same angle, the 36.8699, the same angle, right? This angle here. So this is also equal to angle theta. Okay, so in standard position, it's 36.8699 degrees because measured from the positive x-axis. So theta sub 2, theta sub 2q, rather, is 36.8699 degrees. Okay, so this is the theta sub 2q. Okay, so we can now solve for the total force along the x-axis. So that would be the magnitude of F sub 1q times cosine of theta sub 1q, then plus the magnitude of 2q times cosine of theta sub 2q. Okay, and then for F sub y later, so we can use the sine component. And we don't have yet the values for our F sub 1q and F sub 2q. Okay, so basically they are equal, so we can just write that one time. So F sub 1q is equal to F sub 2q, so let that be equal to F sub q. Okay. then quantity cosine of theta sub 1q. So you can, by the way, solve for f sub 1q separately, okay, or just incorporate it here. So f sub 1q and f sub 2q again are equal because q1 and q2 are equal. So basically it's k times q1 or q2, okay, absolute value of that, and then times q, okay, all over r sub 1q squared. Again, they are equal. Okay, so the distance from q1 and q is equal to this distance between q2 and q. So it's actually the hypotenuse of this right triangle here. So this is the r sub 1q, which is the same with r sub 2q. This is sub 2q. Okay, so this one is the r sub 1q. Again, they are the same because this is also 3 meters from the origin. Okay, so solve for r. So if you can remember, we have this special triangle whose shorter sides are 3 and 4 units respectively. So the hypotenuse is 5 units. It's a 3, 4, 5 triangle. So if you don't know that, or the sides are not 3 and 4 meters respectively, so just solve for the hypotenuse by using the Pythagorean theorem. Okay, so r sub 1q is the same with r sub 2q. They are both 5 meters. Okay, so we can plug in the values to the equation. So that would be 9 times 10 raised to the power of 9 Newton meter squared per Coulomb squared over 5 meters quantity squared times cosine of 323, sorry, 323.1301 degrees plus cosine of 36.8699 degrees. So you don't want to use the absolute value, rather the what you call this, the standard position of an angle. So it's okay. Just make sure that the signs are correct. Okay, so the x component of f sub 1q is positive and the component of f sub 2q is also positive. So it's okay to use the same angle, 36.8699 degrees, because the cosine is just the same with the 323.1301 degrees, right? So you just double the x component of f sub 1q. So we have 9 times 10 raised to the power of 9, then times, or rather divided by 5 squared. So that's divided by 25. Then times quantity cosine of 323.1301. Okay, make sure to enclose that with parentheses plus cosine of 36.8699. Close parenthesis. That's for the second angle, and then you have to put another close parenthesis for the entire expression. So it's 5.76 times 10 raised to the power of, that's 2468. Okay, so 5.76 approximately times 10 raised to the power of 8. In newtons. But that's for the x component of the total electric force. Okay, so let me store that so that we can use the exact value later. So now we solve for the y component. So solve for f sub y. Okay, so for f sub y, it's basically f sub q times sine of theta sub 1q plus sine of theta sub 2q, right? Okay, again, we have a common force because f sub 1q is the same with f sub 2q. So in the PDF file that I shared, okay, the computation is, I guess, different. I solved for f sub 1q and f sub 2q separately. Okay, so this is another way of solving it. Okay, so both are correct. So f sub q is that one, 9 times 10 raised to the power of 9. It's actually the same with that of the x component computation. So it's also 0. What's the, no, it's 5. Sorry, 5 meters quantity square, then times sine of 1 or 323.1301 degrees plus sine of 36.8699. 36.8699 degrees. So that would be equal to 9 times 10 raised to the power of 9 divided by 25 or 5 squared, then times quantity sine of 323.1301, then plus sine of 36.8699. Okay, so basically it's 0. It's actually not necessary to solve for this value because if the two f sub 2q and f sub 1q are of the same magnitude and the angle from the x-axis are the same, okay, so one is just below the x-axis, the other one is above the x-axis, then of course the forces would be canceled out, right? So I'm just showing that they are really equal in magnitude but opposite in direction. So basically the summation is 0. So as long as you can show visually, okay, through a drawing that the two are the same but same in magnitude but opposite in direction. So you can skip this part. Okay, skip the solving for f sub y part. So you can just put f sub y is equal to 0. Then for the resultant, okay, so of course we have the square root of the square of the x component plus the square of the y component. So it's equal to the square root of, so basically it's just equal to f sub x, right? Because this is 0. So let me, so that we won't be writing a lot of stuff. So let's just simplify the equation first before plugging in the values. So since f sub y is 0, so f sub y squared is 0. So it ends up with f being equal to the square root of f sub x squared, or that's basically f sub x. Okay, so it's equal to approximately 5.76 times 10 raised to the power of 8 newtons. Okay, so this is the magnitude, and don't forget the direction. Okay, so the direction would be direction. Okay, so so let me use theta sub r. Okay, because I used theta already. So let me put a subscript r, meaning for the resultant. So theta sub r is, of course, arctangent of the y component over the x component. So y component is 0, x component is 5.76. Basically, this fraction is 0, right? So our tangent of 0, it's 0. Okay, so 0 degrees. So meaning the resultant is on the positive x direction. Okay, so this is the magnitude 5.76 times 10 raised to the power of 8. So basically, the resultant is here, straight along the x-axis. So this is the force, resultant force, total electric force.